All right, today we're going to learn a qualitative technique and a numerical technique for studying the family of solutions of an ordinary differential equation. That's what ODE stands for, remember. So last class we learned an analytic technique that's called separation of variables, but separation of variables is just only applies to a very small fraction of all the possible differential equations in the world. So we're going to learn a couple of other techniques today. So here's a mixing problem. It could be adapted to represent pollutants in a river, or absorption of medication into a bloodstream, or the migrations of species into and out of an ecological system. So this is salt in a tank, which is kind of boring, but like it can be generalized to lots of different scenarios to represent lots of different things. So we're going to try to come up with an initial value problem that then we'll study the solutions to. So at time t equals 0, a tank contains 4 pounds of salt dissolved in 100 gallons of water. And we're going to suppose that the brine, so brine is just a word for salt water, right? Brine containing 2 pounds of salt per gallon is allowed to enter the tank at a rate of 5 gallons per minute. So there's like a faucet going into this tank that has a concentration of 2 pounds of salt per gallon flowing in at 5 gallons per minute. And then the mixed solution is drained from the tank at the same rate, 5 gallons per minute. So we could draw a little picture of the tank here. Tank filled with salt water. At time t equals 0, there's 4 pounds of salt dissolved in 100 gallons of water. And we've got like a little faucet going into the tank. Okay, and it's got 2 pounds of salt per gallon. 5 gallons per minute brine flowing into the tank. And then there's like a little valve at the bottom here, and it's flowing out of the tank at 5 gallons per minute. They didn't tell us the concentration because the concentration is changing as we add salt water to the tank. So that's something we're going to have to figure out. What is the concentration as it's flowing out? Okay, so we're going to let Q represent the quantity of salt. So we have a function Q of t because the quantity of salt in the tank is changing as time passes. So this is going to be quantity of salt in pounds in the tank at time t. And they told us that at t equals 0, how much salt is in the tank? 4 pounds. So that's my initial condition. Q of 0 equals 4. So I've done nothing with derivatives or a differential equation yet. I just defined the function that's going to be my ultimate solution to the differential equation and an initial condition. All right, so if I want to write a differential equation to represent what's happening here, I'm going to do dq dt equals, now I have to figure out the rate in and the rate out. So this is just rate in minus rate out. So salt is entering at some rate and leaving at some rate. You subtract them to get the net change, the net rate of change for the salt. Okay, so dq dt equals, so the rate in, 2 pounds per gallon times 5 gallons per minute will give you pounds per minute. So that's the rate of change of the salt with respect to time. The units on it would be, the Q units are pounds, the T units are minutes, so we need pounds per minute. You get that if you multiply these together. So my rate in is 2 pounds per gallon times 5 gallons per minute. So then your gallons cancel and you get 10 pounds per minute coming into the tank. And then the rate out also has to have units pounds per minute. We have gallons per minute. That's all we know, right? So I'm going to have times 5 gallons per minute. And I've got some other fraction here that represents concentration, right? How many pounds per gallon? So I need to figure out the concentration of salt in this tank because that's what's flowing out. So how many gallons total are in this tank? 100 gallons. And how much salt is in this tank at any given moment in time? Q. Yeah, so that's my concentration. Q pounds of salt in 100 gallons of brine. So your gallons cancel, and you get 5Q over 100, or Q over 20. So I'm just going to write the final equation a little bit simplified. I'll write it up here. So dQ dt ends up at 10. I'm going to leave the units out this time just to make it look simpler. Minus 0.05 Q. Five over 100 is 0.05. And then we always have this. That's part of the initial value problem. Okay, so rather than trying to dive in and solve this thing by separation of variables, what I'm really interested in is the limiting value, the long-term behavior. If you just let this continue for a long, long time, what's the concentration, what's happening to the concentration of salt in the tank? Is it going to increase to infinity? Is it going to decrease to 0? Does it have a limiting value? So what we're going to do is look at something called a direction field or a slope field. So this entails drawing little tangent lines of the appropriate slope at a bunch of different points. So this is the function q of t, right? So I have, it's blank because I don't know what q of t looks like, but I do know what its derivative looks like. Okay, and the derivative represents the slope of a tangent line at any given point. So I'm going to pick some points, calculate the slope of the tangent line, and draw a little mini tangent line at that point. So if I plug t equals 0 and q equals 100 into dq dt, I get 10 minus 5. Sorry, 10 minus 5, which is 5. Just replacing the q in this equation with a 100. If there were a t in this equation, I'd replace it with a 0, but I don't have one in this particular equation. Okay, so at the point t comma q, 0, 100, the slope of the tangent line is 5. So that means I can go to the point 0, 100 on my graph and draw a tangent line that has a slope of 5. Tiny little tangent line that's pretty steep, steeper than 1. So I drew kind of a steep one. All right, so let's see what happens if t is 50 and q is 100. So I'll plug q equals 100 in here and I get 5 again. The 50 didn't matter at all. So at 50, 100, I have a tiny tangent line that's going to have the same steepness as the one I just drew at 0, 100. Anytime q is 100, I'm going to have a tangent line of slope 5. So I'm going to draw them all the way across here, slope 5. All right, now let's say t is 0 or anything, right, for any t. When q is 150, if I replace q with a 150, I get 2.5. 10 minus 150 over 20 is 2.5. So for all t's, when q is 150, I have a slope of 2.5, which is positive. It's going to be increasing, but less steep than the ones I drew at 100. So maybe like that. Little tangent lines that would be tangent to the solution curve. All right, when t is 200, what's 200 over 20? 10, and then 10 minus 10 is 0. So my tangent lines when Q is 200 are 0. They're flat. So at 200, I have flat tangent lines. And when Q is 250, my tangent lines are negative 2.5. So now they're decreasing. Same steepness as the 150, but they're decreasing. So something like this. And then 300 over 20 is 15. 10 minus 15 is negative 5. So I have steeper tangent lines decreasing. So on our slope field, we can sketch some different solutions. So my initial condition was Q of 0 was 4. So when T is 0, Q is 4. So this is like way down here, right? 0, comma 4, because this is 100. So if I were to sort of just follow the slopes, follow these little tangent lines, they are going to lead me up towards the equilibrium solution, the place where the tangent lines are 0. And we can sketch in a few different initial conditions. What if we start with 300 gallons of salt in the tank? If you start with 300 gallons of salt in the tank, what happens? It's going to decrease down to 200. It's going to follow these tangent lines and come down towards 200 gallons of salt. If you start with 200 gallons of salt in the tank, what happens? It stays at 200 forever. So that's why we call that an equilibrium solution. So we are pouring things in and things are draining out. But at 200, even though you're pouring things in and draining things out, the amount of salt in the tank is in equilibrium. It stays at 200 forever. So what does the graph suggest about the long-term behavior of salt? It suggests that the quantity of salt approaches 200 pounds over time as T approaches infinity. So the equilibrium solution is Q equals 200. That is the solution to a differential equation that is constant or unchanging. An equilibrium solution can be classified as a sink, a source, or a node. A sink is when all the nearby solutions approach it, right? Think about like a sink, like everything drains down towards the drain. Everything is going to approach this 200 value, so that equilibrium solution is called a sink. If everything goes away from an equilibrium solution, it's called a source. And if it sort of does like these ones go towards it, but these ones go away, we call that a node. I'll draw a quick picture of. So if this is your equilibrium solution, a source would have all your solutions going away from it as T goes forward. So this is a source. And a node would have some of them approach the equilibrium solution, but the other ones go away. And our example with the 200, that was a sink. Okay, so slope fields are handy for studying the overall qualitative behavior of a solution. They tell us the long run behavior, but they're not as good at answering more specific questions like how much salt will be in the tank after 10 minutes. So to answer those more specific questions, we could solve the initial value problem analytically, separation of variables. But that's sometimes hard, sometimes impossible. So our only analytic tool right now, separation of variables. So instead of doing it analytically, we're going to use a numerical technique. So the numerical technique we'll develop is called Eulers Method, named for Leonhard Euler. It gives us a precise way to draw a particular solution by following the slope field. It takes advantage of the fact that the tangent line approximates the solution curve near the point of tangency. So let's just think about slope for a minute. If you know that the slope of this line is 2, and you know delta x is 3, what does delta y have to be? 6. Yeah, change in y over change in x gives you slope. So delta y would have to be 6. So in general, since m is delta y over delta x, then delta y is slope times delta x. Just multiply both sides of that slope equation by delta x. All right. This is a pictorial description of Euler's method. So the solution, we have a function y of x that's going to be a solution to the differential equation dy dx equals negative 2x plus 6. So we could just solve that. We know that the answer is just the antiderivative, negative x squared plus 6x plus a constant, right? The solution to this differential equation is easily solved analytically. You could find the constant by using the 0.24, the initial condition. All right, but let's pretend we know nothing about the solution, just so that I can show you this method. So the solution is this parabola, right? It's the negative x squared plus 6x plus a constant. So I've drawn the solution in for demonstration purposes, and I've drawn a tangent line to the solution at the initial condition. So 2, 4 is given, and the differential equation is given. So if you know a point, you can plug it into the differential equation to get the slope of this line. Right? So the slope of that line is dy dx evaluated at 2, 4. So that is f. The slope of that line is 2. So from our choices, the slope of the line is the differential equation evaluated at the point 2, 4. Remember, the differential equation is dy dx equals negative 2x plus 6. So if you plug a 2 in for x, you get negative 4 plus 6, which is 2. So the slope of the tangent line is 2. So if you know a point and you know the slope, you could know the equation of this line. So we can graph this line, this tangent line, even though we don't know the solution curve. All right, number 2. Next thing I want to fill in, the distance from 0 to 2. That is x naught, which is g. That is my initial condition, x naught. So just scroll down a little bit and look at g. X naught is 2, because your initial condition is x naught, y naught. Okay, so 3 is the y value. It's the distance from 0 to 4. This is 3. So 0 to 4, that's y naught, which is 4d. Okay, number 4 is this horizontal distance from 2 to 3. From 2 to 3. So let's see what my options are. It's not a y value. It's not a change in y. It is a change in x. It's a change in the x value by 1. So from my initial condition, x naught, I moved over 1. So it's my delta x value of 1. So that's C. Number 5. This is a change in the y value. From my initial condition of 4, we jumped up a bit. So this is my delta y, which is 2. Delta y, which is slope times delta x. So let's just scroll down and look at that a little bit. Delta y, you can calculate by doing the slope of the tangent line times the change in x, right? Because delta y is always slope times delta x. So I knew the slope was 2, delta x is 1, so you do 2 times 1 and you get a jump of 2. Okay, number 6 is the distance from 0 up to 6. So it is x, so it's your original y plus delta y. Y naught plus delta y. That is my estimated value for y of 3. 6. So that's B. So when you go over here, that is the y value on the tangent line. So y value on the tangent line. All right, and then 7, this is the actual y value, y of 3. And the actual y value, y of 3, that's A. So we have an estimated y of 3 and an actual y of 3, and there's some error, right? We're using the y value on the tangent line to estimate the y value on the curve that we don't know. So numerically, this is how Eulers' method works. So we have this chart. I have columns for my x values and my y values, the slope at each of those x and y values. Then I'm going to calculate delta y, which is always the slope times delta x, which in this case, we're going to use delta x as 1. That's something that's always given to you, the size of delta x when you're doing these problems. And then your new y is your old y plus the change in y, delta y. Okay, so my i's are changed. These are my I values. So x0, y0, that's your initial condition. 2, 4, that's what we were told. 2, 4 is a point on the solution curve. The slope at that point, you plug 2 and 4 into the slope equation, and you get 2. -2 times 2 plus 6 is 2. And then your delta y, that's your slope times your delta x, which is 2 times 1, which is 2. Delta y is 2. And then your new y is your old y plus your delta y. So 4 was my old y. My change in y is 2. So my new y is 6. This row is all the stuff we labeled in the picture. That row is the entire picture. And I can continue to do this process where I now have a new y, 6. My new x is 3 because my delta x is always 1. I'm always going to increase my x values by 1. And then to get my y's, I have to fill in all this stuff as I go across. So my next point is 3, 6. That is this point right here. This is the point we just found, 3, 6. So now I'm going to use 3, 6 as my next point. I'm going to assume it's on the curve or very close to on the curve and do the whole Eulers process again. So I plug 3 for x and 6 for y into the formula for dy dx. So -2 times 3 is -6 plus 6 is 0. Delta y is your slope times delta x, which is 0. So my new y is my old y, which was 6, plus my change in y, which is 0. So I get 6 again. That's just, it was given. I didn't make it clear, but you'll always be given the size of delta x. Yes.
Are you choosing your y's?
My original y's? Yes, I'm taking it from the previous, yeah. So 2, 4 was given, right? 2, 4 was the given initial condition. So then my new y is my old y, so 4 was my old y, and then I add my delta y, 6. So I take this 6 and move it down here. Okay, we'll do one more iteration and see where we end up. So plug 4, 6 into the dy dx formula. So -2 times 4 is -8, plus 6 is -2. Delta y is the slope times delta x, so -2. And my new y is my old y, which was 6. That's the y I was just using. Plus my change in y, -2. So my new y is 4. Put that down here. So I have 4 points now. 2, 4, 3, 6. 3, 6 I already came up with in the picture. Right? Now I have 4, 6, and 5, 4. I'm going to plot them in the picture. Okay, so 4, 6 is about here. And 5, 4 is about here. So these are the points that Eulers' method found. So 2, 4 was the given, the initial condition. That is definitely a point on the solution curve. And then Eulers' method is estimating more points. It's trying to find more points on the solution curve. So if you connect these with straight lines, you can see it is trying to approximate a parabola, which is the solution curve. It's not doing a great job, but it does know some stuff, right? Like the tangent line right here on the actual solution curve is flat. And Eulers' method knew that. It's got a flat chunk right here. And it is creating a parabolic shape, but my errors are compounding, right? It's not a super great method. If I wanted it to be better, I could do smaller jumps, or I could make delta x smaller. Because if I used this point on the line to estimate this point on the curve, that would be a very small error. But using this point to estimate this point, that's a pretty big difference. So that's the general method of how you do Eulers' method. And I'm going to have you do some practice. I'm actually going to have you do the group activities in a different order than they're presented. I want you to do 5, 6, 4, 1, 2,